In the last video, we developed Newton's second law for rotations, and so I'd like to start here by doing an example. So in this example, I'm imagining that we've got a large disk, 2 meters in radius, 10 kilograms, that we've run a string over and are attaching to a 5 kilogram mass. Initially, the mass is at rest, and we're just going to let it fall. I'd like to know what the acceleration of the mass is. So we can start by applying Newton's second law of motion to the small mass. So we can make that one of our systems there. We can draw a free body diagram for the small mass. And we see that the force of gravity on the small mass would be acting down. Tension in the string would be acting up. We know that the net force has to point down because intuitively we know the acceleration points down. So when it comes time for us to go ahead and write Newton's second law for this system, we will go ahead and choose down to be positive. For the disk, though, I'm going to choose to draw an extended free body diagram. And the reason for this is that just plain doing the translational Newton's second law isn't going to be too useful here for us. This is because we will have a normal force up from the axle holding the wheel. We will also have a force of gravity down, and we will have a force due to tension down. Now, we don't know the force due to tension, and we don't know the normal force. All we know is that the three forces together are going to add up to 0. So looking at the sum of the forces is not going to be the most useful thing, but looking at the torques is going to be useful. Let's go ahead and put our rotation axis right here. By doing this, we have the lines of action for both the normal force and the force of gravity passing through our through our rotation axis. And this time here it's particularly convenient because this is actually the axis it's going to rotate about. Now we know that the angular acceleration is going to be clockwise. So for this problem here, I'm going to choose positive to be clockwise rotation just to make these signs easier to handle. All right. So let's go ahead and start writing down Newton's laws of motion for this and see how far we can get. So for the mass, we can just go ahead and do Newton's second law, and we will say F net y equals little ma. And technically a sub y, but the acceleration is purely in the y direction. And we've already chosen down to be positive, so that takes care of the direction. So this will be the force of gravity on the little mass. I should have said here on the big mass. Minus the tension equals little ma. And that's about as far as we can take that. Here, like I was alluding to before, looking at the net forces in y, we know it's going to add up to 0, but it's not going to be very useful for us unless we want to find the normal force from the pin, but we don't really need to here. So we'll say sum of torques equals I alpha. All right, we've only got one torque, and it's the torque due to tension. And the lever arm for this torque is going to be the radius of the wheel. Here's the line of action right here. Let me just go ahead and draw in the line of action in green. The lever arm is always the shortest distance from the axis to the line of action. So there's my lever arm. It's the radius of the wheel. So we said that clockwise is positive, so we can have a plus sign here in front of my alpha, and my only torque is going to be due to tension. It'll be the force is the tension, the lever arm is the radius, so T times R equals I alpha. Now, the one thing we do know is that these tensions are an action-reaction pair by the third law. So we can eliminate the tensions between these, hopefully. All right, now it may seem like we're in a pickle here, and that's because of this angular acceleration is not the same thing as this linear acceleration. But all's not lost, we can relate these. So let's take what we've got so far. What we've got so far is TR equals I alpha, and we have FG on the little mass minus T equals little ma. We can say this is little mg minus T equals little ma, and this is as far as we can take it until we do more over here. Now, we said this is a disk. If you look up moments of inertia in a table, you'll find that the moment of inertia of a disk is 1/2 the mass of the disk times r squared times alpha. So we can cancel 1 power of r. Now here's the cool bit. If we look at this point here at the end of the wheel, right? Its tangential acceleration has to be equal to the acceleration of the mass here. This is because if it weren't, let's say it was less, then this would be gaining ground over whatever this was doing. It would mean the string would have to stretch. And similarly, if this acceleration is greater than this, the string would start like piling up between these, which doesn't make any sense either. So this acceleration, the tangential acceleration of this point right here, there is a centripetal component as well, but we don't need to worry about that at the moment. The tangential acceleration of this point on the rim right here will be the acceleration of the piece of string right here, and that's got to match the mass, or else we're not going to be moving at the same rate. So we can observe that that's equal to a. But we know the tangential acceleration is equal to r alpha. So when we look here, we see an r alpha, and we can observe that that is the acceleration of our mass. Cool. So now we've got an expression just in terms of the tension. Get that the tension in the string is 1/2 the big mass times our common acceleration. We can take that and insert it over here to eliminate our unknown tension. So that's going to give us mg minus 1/2 big Ma equals little ma. Okay, rearranging, we will have little m plus big M over 2 a equals little mg, or a equals little m over little m plus big M over 2g. All right, so this was 5 kilograms over 5 kilograms plus 10 kilograms over 2 times 9.8 newtons per kilogram. And here, since this is going to become an acceleration, we can write that as meters per second squared. All right, kilograms, numerator and denominator will cancel out. I've got 5 over 10 times 9.8 tells us that the block will be accelerating at 4.9 meters per second squared. All right. So following along here, it would be nice if we could also do some energy conservation type stuff. And following a similar analysis to what we got for Newton's second law for rotations, we can say that our kinetic energy can be broken into translational, KE, T plus rotational kinetic energy. So this is the kinetic energy associated with the bulk motion in the center of mass. This is the kinetic energy associated with the rotation about the center of mass. The translational kinetic energy is still 1/2 mv squared like before. And the rotational kinetic energy turns out to be 1/2 I omega squared. So for instance here, we can do a problem where, say, we go ahead and let a bowling ball, mass doesn't matter, radius doesn't matter, we go ahead and let a bowling ball roll down an incline that is, well, let's say 10 meters high, just to make the numbers straightforward. So now when we do our energy conservation, we still can make a table, final, initial. So we're going to want to put y equals 0 at the bottom. So then this here would be y initial is equal to the height up here. All right. So now when we write our kinetic energy, we'll have Ke translational, Ke rotational, and we will have gravitational potential energy. So our translational kinetic energy is 1/2 mv squared. Our initial is 0. Our rotational kinetic energy is 1/2 I omega squared. Our initial is 0. Our final gravitational potential energy is 0. Our initial is mgh. Okay, now if the ball is rolling without slipping, which is what you usually assume if something's going down a ramp, it turns out that we can relate the angular velocity of the ball to its translational velocity. So if it's moving to the, let's say, to the right, velocity v, in order for it to roll around, if you think about it, if you're not slipping, at this exact spot right here has to be instantaneously stationary. So the only way that can be the case is in the perspective of the frame of the ball. So here, this is in the ball's frame. This is from the side. From the ball's perspective, it's seen the road move past it at v to the left. So it would have to be saying, okay, this point here, in order to maintain contact to the ball, it would have to be spinning such that this tangential velocity here is v. Here, and for that matter, there, and anywhere else we would like. So when we add these together, so in the frame of the of us watching it, we'll be adding v to all these points. Here, let me get rid of this just to clarify it. We'll be adding v to all these points. This one will cancel to give us our stationary point as we see it, and this one will be moving at v. Now the only way this is going to happen is if this tangential speed here, tangential velocity here, is the velocity of the center of the ball. So the condition for rolling without slipping is that v equals r omega. This is only true if you're not slipping. If you are slipping, then all bets are off and you can do whatever you want. All right, so with that caveat in mind, let's go ahead now and do the energy conservation. So we've got a 1/2 mv squared plus 1/2 I omega squared equals mgh. Now, if we go ahead and look up a sphere, the moment of inertia of a sphere is 2/5 mr squared. So let's go put that in. So 1/2 mv squared plus 1/2 times 2/5 mr squared omega squared. That has to equal mgh. First small favor, the m's all cancel. Cancel there. So we've got 1/2 v squared plus 1/5. Now r squared omega squared is the same difference as r omega squared. That has to equal gh. Now r omega, since we said that we're rolling without slipping, has to be equal to v. So this becomes 1/2 v squared plus 1/5 v squared equals gh. Cleaning that up, that is 7/10 v squared equals gh, or v squared equals 10/7 gh, giving us a final speed of root 10/7 gh. Now, if you think about a problem where, say, we had a hockey puck slide down a similar ramp, instead of a 10/7 here, you would have had a 2. So because we're rolling, our final speed will be lower than if you're just plain sliding. And this is because some of the energy went into making all the mass of the bowling ball move around the bowling ball. Okay, so let's go ahead and put in the numbers. This is the square root of 10/7, 9.8 newtons per kilogram. And again, here for dimensional analysis, turning this into meters per second squared is fine. And then we said that our ramp, just to make the problem straightforward, was 10 meters. So punching that into our calculator, there we go. That will be 11.8 meters per second. Now you should ask yourself, if this were a disc instead of a bowling ball, would the final speed at the bottom of the ramp be faster or slower than 11.8? So pause and think about that for a sec, and then I'll get back with you. Okay, so it turns out that if it's a disk, because a disk has a higher moment of inertia, that means that the average molecule is farther away from the axis. All those molecules are going to have to be physically moving faster because they're farther away for a given angular velocity, because v equals r omega. So that means a greater share of the potential energy will have to be converted into translational. So less of it will, or sorry, into rotational. So less of it will go into translational. And so we will have a slower speed than 11.8. Alrighty. So before we get to the final form of Newton's second law for rotations, I need to introduce angular momentum. Now, I will go ahead and put in all the caveats right now. Turns out that expressing angular momentum is actually a fairly hairy thing, and you have to take a lot more care about it in more advanced treatment. However, it turns out that for three major situations, which cover almost everything you're ever going to care about, except for almost everything you're going to care about. You can treat angular momentum as a scalar. Normally you can't, but you can here. And you can say that the angular momentum of something, we use the symbol L, will be equal to the moment of inertia of the thing times its angular velocity. Now, the reason I was kind of waffling here a bit is because there is a little more to it than that. If you've got a small, lightweight box, none of whose sides are the same length. So for instance, like a tissue box or something like that. Just to give you an idea that there's a little more going on here than meets the eye. Try tossing the tissue box up in the air while giving it a spin around its different axes. So if you spin it around its long symmetry axis, you'll find that it spins in a very orderly way as it flies in the air. And similarly, if you give it a spin about its short axis, same deal, it'll spin in a very orderly way. But if you spin it about the axis intermediate in length between the two, it will tumble around in a really weird way. And this is because, in general, you have to treat angular momentum as a vector, and things can get a little hairy. But if you're rotating about the long or short symmetry axis, which most of the time that's what you're worried about, this expression is just fine. So our units of angular momentum, if we follow it all through, are going to be kilogram meters squared per second. All right. I introduced this because, as you're probably expecting, there is a more accurate statement of Newton's second law applied to rotations. It follows a similar but a little hairier analysis to what we did before to get that the net torque is equal to I alpha. And the more generally correct version should be reminiscent of the more generally correct version of Newton's second law, which is that the net torque on something is equal to the time rate of change of the angular momentum. Now, if the moment of inertia of the object is not changing with time, this works out to be the I alpha that we were dealing with before. Now, there are different reasons why the moment of inertia could change. One, you could have a system whose mass is changing. For instance, we could be worrying about a spinning raindrop as it falls through the sky or something picking up water. And that seems pretty far-fetched, and it is. But it's not far-fetched at all for the moment of inertia to change because the distribution of matter changes. For instance, if you think about a figure skater, if they go and do a spin, they can voluntarily change their moment of inertia by how they hold their arms out. When they start the spin, usually their arms hang out far and give them a large moment of inertia. And as they pull their arms in, their matter is getting more concentrated towards the rotational axis, decreasing their moment of inertia. Their mass doesn't change, but their moment of inertia changed because they changed how their matter was distributed. So generally speaking, to do an analysis when the moment of inertia is changing would involve the methods of calculus and be beyond the scope of this treatment, but there is one case that we can look at. If the net external torque is 0, then you can conclude that the change in angular momentum has to be 0. And from that, you can conclude that the final angular momentum is equal to the initial angular momentum. So to do a concrete example of that, let's say you happen to have a Formica table or something, or, a piece of, let's not do Formica, a piece of wood. You drill a hole through the piece of wood to let a string hang out. And then you go and tie a washer to the piece of string. And let's just say initially the radius of the string, let's say our initial here, is equal to 1 meter. And that initially we have the washer orbiting around at 10 radians per second. Now, you grab underneath the tabletop and you tug on the string. And in so doing, you shorten up the orbit until the new radius, our final, is equal to half a meter. So now you're going around in a smaller circle. Can we find the final angular velocity? And the answer is yes. So here for our system is the washer. Now, 2 of the forces acting on it we don't really have to care about. The normal force pointing out of the screen toward you and gravity pointing into the screen away from you. Those will cancel out in our analysis. What does count is the tension in the string pointing into the center. However, our rotation axis is right here. The tension in the string is the line of action for the tension in the string is right along the string itself, going right through that axis. So, although the net force on the washer is not 0, there is this unknown force due to tension. The net torque on the washer is 0. So because the net torque on the washer is 0, we can demand that the final angular momentum equal the initial angular momentum. So this will be I final omega final equals I initial omega initial. So we get that omega final will be I initial over I final omega initial. Now for a washer is compared to a half a meter or a meter's radius. A washer can be well treated as a point mass, and the moment of inertia of a point mass about some axis is mr squared. So putting that in, this would be the mass of the washer times r initial squared over the mass of the washer times r final squared omega initial. Cancel, cancel. If you want, you can make it a little prettier by saying r initial over r final quantity squared omega initial. All right. And so then we said 1 meter over half a meter squared times 10 radians per second. Well, this is just 2. Squared is 4. times 10 is 40 rad per second. Now, something to think about here is if you grind it through, you will find that the rotational kinetic energy of the washer increased. So you should ask yourself, what did work on the washer to make that rotational kinetic energy go up? Think about that for a second and I'll get back with you. All right, so the answer here is that the tension in the string moved the washer. So there was a displacement in the direction of the force, that is positive work on the washer. So the extra energy, so energy got input into the system by the work that tension did on it. A handy thing for thinking about work, a professor of mine way back in the day would say, ask yourself what ate breakfast. In other words, something had to consume some sort of energy somewhere. So here, my hand would be pulled on the string. I'm something that would have eaten breakfast in the morning. I pull on the string, I do work on the string. So ultimately the energy came from me pulling on the string for the work that I did doing that. If that's helpful, great. If it's not, that's okay too. Alrighty, so with that, we will, we're good with this topic, and I will catch you in the next one in cyberspace. Catch you later.